Hello, my name is Fernanda Sobral, and today I'm going to solve the problems from the first partial exam. So the first problem says, Donald Duck and his nephews managed to sink Uncle Scrooge's yacht with a mass of 4,500 kilograms, which is made of steel, with a density of 7,800 kilograms per cubic meter. In typical comic book fashion, they decide to raise the yacht by filling it with ping-pong balls. A ping-pong ball has a mass of 2.7 grams and a volume of 3.35 times 10 to the minus 5 cubic meters. So, part A is to calculate the buoyant force of one ping-pong ball in water. So, well, here I drew a small diagram where we can see the boat and the ball, and we have the information for each one of them. So we know that the buoyant force equals the mass times gravity. So in this case we can change the mass for the density of water according to this formula, which is in which the liquid in which the ball will be submerged times the volume of the ball times gravity. So we know the mass of water is 1,000 kilograms per cubic meter. We have the volume here, and we have gravity as 9.81. So our result should be 0.3286 newtons, because it is a force. So that's part A of the problem. And part B says how many balls are required to make the ship float. So in this case, we know that there are two ways to calculate the buoyant force, as mass times gravity, or using what I just did, which is the density of the liquid times the volume. So we can reach like this conclusion, that the buoyant force can either be calculated, the total buoyant force, because we need to take into consideration that both the balls and the ship are floating, can be calculated as the number of balls that we will use, which is what we want to find, times the density of water, times the volume of one ball, times gravity, plus the density of water times the volume of the ship, which in this case we'll take as steel, times gravity. And this should be equal to the total mass, which is n times the mass of the balls, plus the mass of the ship times gravity. So from here we can take out n. And when we solve for n, we have that in total we will need 127,373 ping-pong balls to raise the ship again, well, the boat. So that's it for problem 1. Problem 2 says, a large storage tank open at the top and filled with water develops a small hole in its side at a point 16 meters below the water level. If the rate flow from the leak is 2.5 times 10 to the minus 3 cubic meters per minute, determine A, the speed at which water leaves the hole, and B, the diameter of the hole. So for this we can use the continuity equation, and well, I'm making a small diagram in this case as well, so that we understand this. So okay, we're going to use both Bernoulli's law and the continuity equation. So for A, we need to calculate the velocity at the speed at which water leaves the tank here. Let's say this is water leaving the tank, okay? So we have Bernoulli's equation, and we know that we're going to compare these 2 points. Pressure here is the same, so we're going to take only the rest of the equation. And we know that when we do this, we end up eliminating the density, so we end up with something like this. Okay, so we are going to take sorry. This point is 0 and this point is 16. So we're going to take, and the velocity here is almost 0 because it's not actually moving. So this should equal 0, this should equal 0 as well, and we end up with this. So when we solve for v2, we know that it's equal to the square root of 2 times gy1, which is 16. So the value for this velocity should be equal to 17.7 meters per second. So that's the first part of the problem, the velocity at which it leaves the hole. So the second part is to calculate the diameter. We know that the rate is equal to rate equals 5 times 10 to the minus 3 cubic meters per minute. And we have to have everything in seconds. So we need to pass this to seconds, and we do this by dividing by 60. So this ends up being equal to 4.167 times 10 to the minus 5 cubic meters per second. So once we have this, we know that the rate should be equal to the area times the velocity. So area should be equal to rate divided by velocity. So we divide this by the velocity we calculated before, which is 17.7. And we obtain a total area for this hole of 2.354 times 10 to the minus 6 square meters. So from this we can use the formula for the area, which is pi times the radius to the square, and we solve for r. So we know that the radius should equal the area divided by pi, square root of that. So once we substitute this value here, we end up knowing that the diameter, and we should multiply this by 2. So for example, if we want for the diameter, it's 2 times this, right? So we end up knowing that the diameter equals 0.0017 meters, or 1.97 millimeters. So that's the final, well, the second answer for the second problem. And finally, problem number 3 says, a clock uses a physical pendulum which consists of a uniform thin rod with mass m and length L that is pivoted freely around about one end, with a solid sphere of radius L divided by 2 and the same mass. M centered about a free end of the rod. So part A asks us, what is the rotational inertia of the pendulum about its pivot point in terms of M and L? So I'm going to copy this little diagram that was provided in the exam. I hope it's good enough. So here we go. More or less like this, right? And it's moving like this. So first of all, to calculate the rotational inertia, we are going to, well, the problem provided the rotational inertia for a rod length, which is a rod with length L, which is 1/3 of ml squared, and rotational inertia for a sphere of radius r, which is 2/5 of mr to the square. And we're going to use the parallel axis theorem, which says that I should equal the rotational inertia of the center of mass times m d to the square. Okay? So this should be the addition of the rotational inertia of the rod plus this part for the sphere. As we know that the mass center is located about here, which is 3/4 L from the pivot. Because, well, this is L, this is half of L, so this should be 3/4 of L. So at the end we have that I total should equal the rotational inertia for the rod, which, as I said, is 1/3 of ml squared plus the rotational inertia of the center mass of the sphere, which is 2/5 m to the square, because this is the radius of the sphere, plus m diameter squared. And the diameter of the sphere is 2 times L divided by 2, which is L. So we can add this up. 1/3 plus 2/5 times 4 times 1/4 plus 1, and we end up knowing that this equals 43 divided by 30 ml squared. So that's the first answer for our problem. The second part says, for a period t equals 2 seconds, what should be length L? So for this we can use the formula, which equals, I'm writing it here, so it's this, okay? This, where we have the period here, the total rotational inertia, the mass of the system, and the distance from the pivot to the center of gravity. So what we want to know from this is, no, I'm sorry, I read the wrong question. No, letter B is, what is the period of the pendulum for small oscillations? So we're going to substitute this formula, well, whatever we got before, which is that the total rotational inertia is 43 divided by 30 ml squared. So we're going to substitute this and all the information we have here in here. So we know that T should equal 2 pi divided by 43 divided by 30 ml squared divided by the total mass, which is 2m, times gravity, times r, which is this distance, which is 3/4 of L. So this should end up being equal to, we can cancel this out here, and we make these the appropriate calculations. So this should be equal to this right here. So this is what expresses the period of the oscillations of the pendulum. So finally, it's asking us, as I read before, for a period t equals 2 seconds, what should be the length L? So we can use the formula we obtained just before. So like this, 2 seconds, right? So we know that 2 should equal 2 pi divided by 43 divided, square root of 43 divided by 45, L divided by G. So what we need to do here is solve for L. So we know that 1 over pi to the square multiplied by 45 divided by 43 multiplied by G should all be equal to L. So here we just solve for L. Yes. And we obtain a value for L of 1.04 meters. And that's our final answer. This is how long this distance should be in order for the pendulum to have a period of 2. And that's all for the exam. Thank you very much.